Hi, everyone. My name is Ritvik Sehjwal. I am an associate research professor at the University of Maryland, and I'm here to talk about optimization of crop cuts in an insurance context. So this workshop is about food security, doing crop yield forecasting, and in this context, crop cuts enable agricultural assessments. They involve marking a subplot within the field and subsequent measurement of production in the area to get a field scale estimate. As you can imagine, that's way cheaper than doing a full field scale harvest. Now, accurately determining crop yields at field scale, as you can imagine, can help farmers estimate the net profit, enable insurance companies to ascertain payouts, and when aggregated at regional and national scales, this is critical in ensuring food security. Now, over the last few decades, crop cuts have been widely used to estimate field scale crop yields. They're considered more reliable generally than farmer recall estimates when you ask a farmer, what yield they got last year or the year before that. And they can be cost prohibitive, but they are much less so than full field harvests. Now, in this context, there is a saying that nothing is enough for the man to whom enough is too little. And this talk is all about finding out how many crop cuts are enough. Optimizing the number and the location of crop cuts can drive down costs while maintaining the capacity to accurately predict crop yields and conditions. So in this context, NASA Harvest, Swiss Re, an insurance company, and Green Triangle, a small agronomy company, collaborated to collect crop cut information on crop type, planting date, yield, and condition for 6 major crops: wheat, maize, soybean, barley, sunflower, and canola in Ukraine in 2018 and 2019. Several agronomists were hired to collect this information for pre-identified fields, and that's critical that these fields were pre-identified because they defined the universe of possibilities in which we explored the optimal solution. There's quite a few logistical challenges involved. Ukraine is a fairly large country, about the size of Kansas and Colorado put together. And the folks who went out to collect this data, they collected not only the yield information, they assigned some sort of crop condition information as well. And as you can see in this graphic, for the different crops, the estimated condition matched well with the yields. And in terms of the challenges involved, this is a picture that one of the agronomists sent us where he was trying to go to a field and couldn't really make it because of the potholes in the road. So there's actual good we can do in terms of the optimization and trying to reduce the amount of traveling they have to do. So the size questions in this presentation include looking at the choice of remotely sensed vegetation indicator, what would work best in terms of crop yield forecasting, yield modeling, how can these indicators be combined with machine learning models to forecast yields, and finally, optimization of the crop cuts. How can we reduce optimize the number and location of the crop cuts to drive down costs and still maintain model accuracy? So in terms of the satellite data that we used harmonized Landsat Sentinel data set, which combines Landsat and Sentinel at 30-meter resolution. We cleaned and interpolated this data set using a non-parametric Savitsky-Golay approach to determine a smooth upper envelope. And once we got these smooth upper envelopes, we looked at various metrics. We looked at NDVI, which is really popular in remote sensing literature, and we also looked at GCVI, or Green Chlorophyll Vegetation Index. And we found that GCVI offers much better separability across poor, average, and good performing fields as compared to NDVI. The graphic that you see on the right is NDVI, and notice the squishiness. This indicates that the satellite is not really able to distinguish between these poor, average, and good performing fields as well as it can do in terms of the GCVI metric. Next, we wanted to predict crop yields based on the properties of the GCVI time series. So we built machine learning models to predict crop yields at field scale, and we used 13 features derived from the time series information. We looked at some very obvious metrics like value of GCVI at the peak of the curve, area under the peak, time needed to attain the peak, count above and below the mean, longest strike above mean, longest strike above mean, and a few other metrics. The idea was to characterize the time series as well as we possibly could for the fields and for the crop cuts that we had. And then we compared several machine learning algorithms on these features. We used linear regression, lasso regression to constrain the features, the selection of features, so that we can get a parsimonious model. We used random forests, and then we also used a variant on random forest called QBEST, which tends to extrapolate better than random forests as it fits a linear equation at the leaf nodes. And this is really helpful, especially in terms of doing yield forecasting, where you can very often get extremely high or low yields. And finally, we also included mixed effect random forests, which is a relatively new development which combines mixed effect models with random forests. And it's particularly relevant if there is some sort of structure in your data or some sort of clustering. For example, in this case, we can imagine that the yields have some sort of clustering at regional scale, right? So yields in one particular county or state might be more similar to one another than yields in northern Ukraine or yields in the very south of Ukraine. Then we built several machine learning models using the scikit-learn library in Python. We had about 170 fields in 2018 and 330 fields in 2019 that we used to train, test, and validate the model. We used nested cross-validation to avoid high variance in performance estimate due to the small size of the test set. And we used grid search to determine optimal model hyperparameters for each machine learning model. So in terms of the optimization itself, we wanted to minimize the distance traveled and also the number of crop cuts that were to be performed. So we decided to optimize the length of the minimum spanning tree that connects all the crop cut sites. You know, there were other metrics that could have been used as well, but minimum spanning tree seemed to be a good one in this particular context. And for the optimization itself, we use genetic algorithms, which are a popular and fairly fast way to determine the best possible global maximum or minimum when you could have potentially a very large search space. So we use genetic algorithms to optimize the number and location of crop cuts by minimizing the length of the minimum spanning tree connecting those crop cuts. So this automatically reduces the number of crop cuts and also tries to find crop cuts that are closer together. Finally, these are the results from the multiple machine learning models that we used: linear lasso, random forest cubist, and mixed effect random forests. When using data from the fields that we had, we generally got R squares of around 0.67 and RMSE of around 1 ton per hectare. But something interesting happened when we started to reduce the fraction of crop cuts that were available for the model. So what you see here in the graph on the x-axis is the fraction of crop cuts that we used, and on the y-axis is the model R-square value. And what you can see is when you have all the crop cuts, your R-square is approaching 0.7, especially for example, mixed effect random forest. But as you start reducing the fraction of crop cuts that are used, the R-square values start dropping. And depending upon where you are in terms of the number of crop cuts, you get very different looking network configurations because you're looking at different minimum spanning tree configurations. So at the very right is the fully fleshed out network where you went to all the fields, collected all the data. And on the very left is where you use a very small fraction of crop cuts, but the model performance is really poor as well. The sweet spot is somewhere in the middle where you reduce the number of crop cuts, but you still achieve a reasonable amount of model performance. And this performance varies by model, of course, with the mixed effect random forest performing the best. So our results indicate that we can reduce the minimum spanning tree distance by 22% from about 7,000 kilometers to 5,000 odd kilometers without significant reduction in model performance as indicated by the RMSE and R-square values, and as you can be seen from the graphic over here. So in summary, crop cuts offer a very effective, cost-effective method to enable agricultural yield assessments, and certain metrics like GCVI outperform others. Now, this is common knowledge, but what we also found was that in this particular study, mixed effect random forests and cubists tend to outperform the other models for yield modeling, and that we could combine that with the genetic algorithm, and that I think is the novelty of the study to find the optimal location number of crop cuts. And we were able to do this and reduce the distance traveled to collect crop cuts by about 22%, and the number of fields visited by 40% without sacrificing model performance. Thank you very much for listening to me, and my email is below. Please feel free to get in touch if you have any questions. Thank you. Bye-bye.